Now, let's discuss what a radar observes. We've gone over some of this before. We know that a radar transmits a signal, which is typically represented as an idealized square envelope for one pulse. The transmitted signal goes out, reflects off the target, which we'll assume is moving at a constant velocity v, toward the radar along the radar's line of sight. For now, we won't consider targets moving across the radar. We'll address that later. The echo from the target scatters back to the radar. The form of the transmitted signal is an amplitude that changes over time. Before the signal is received, there's no detection, but once the signal returns, we get an exponentially decaying complex signal that lasts for a while and then goes to zero. However, the signal received is not the same as the transmitted one. It is attenuated and delayed because of the time it takes to travel to the target and back. This delay, denoted by tau, must be subtracted. Additionally, the frequency of the received signal changes due to the Doppler effect. The range to the radar from the target is its initial range at t equals 0, minus the velocity of the target multiplied by time, as the target is moving toward the radar. The Doppler effect causes a shift in the frequency of the received signal, which I'll explain further in another diagram. We can measure several important parameters from the received signal. The amplitude of the echo depends on the radar cross-section of the target. The power of the radar, the distance, range to the target, and the directionality from the antenna, which should ideally have a narrow beam width, allow us to determine the azimuth and elevation with certain accuracies. The time delay gives us the range to the target. Finally, the Doppler frequency shift is twice the radial velocity, or the velocity along the radar's line of sight. It is calculated as the velocity of the target multiplied by the transmitted frequency, divided by the speed of light. Since frequency divided by the speed of light gives the wavelength, the Doppler shift can be expressed as twice the radial velocity divided by the wavelength of the transmitted signal.